Hi, everybody. Welcome to the C3.ai DTI workshop on data, learning, and markets. We are very excited to welcome you all to the campus of the University of Illinois at Urbana-Champaign. We've had many workshops, but they were all online, so this is the very first in-person, super exciting workshop. Thank all of you for coming here. Just to give you a few words about the DTI, so this is an institute that was formed in February or March of 2020, just at the beginning of the pandemic. So it's a jointly headquartered institute at Illinois and Berkeley. My name is Srikanth. I'm the director on the Illinois side. Shankar Shastri is the director on the Berkeley side. We have two co-chief scientists, Tandy Warner here and Kostas Spanos at Berkeley. The institute was made possible by a generous donation from C3.ai. It's an AI company specializing in enterprise AI. And a generous donation of computing support from Microsoft Azure, and also computing support from National Center for Supercomputing Applications, which is the building we are in, and from the Lawrence Berkeley Labs in Berkeley. So our goal is to promote the use of AI and machine learning for the digital transformation of society. What that means is basically we want AI and machine learning to be useful to the benefit of humankind. Whether it's academia, politics, business, science, so wherever we can use AI and machine learning to make life better for everybody. We also have a number of academic partners: MIT, Stanford, University of Chicago, Princeton, CMU, KTH. I don't know if I'm leaving out anybody. I think that's it. And some academic and some industry partners like Shell. So today's workshop is on, or the next 3 days workshop is on data, learning, and markets. And I'd like to thank Eric and Rasul for putting together an excellent program. And I'd also like to acknowledge Larry and Jay and Stacy for organizing the local arrangements and everything. So without further ado, I'd like to turn it over to my distinguished colleague and eminent game theorist, Professor Tamer Bashar, to chair the first session.
Thank you, Srikanth. I also congratulate the organizers for lining up such a distinguished list of speakers. And this is a very sort of timely topic, and it definitely also interests me a lot. So I'll be chairing this first session, and we have three speakers. And the first speaker is Professor Vijay Vazirani, who is from University of California, Irvine, I believe Computer Science Department. And he received his undergraduate degree from MIT and his PhD from UC Berkeley. And he has made fundamental contributions to several areas which are very relevant to this workshop: theory of algorithms, matching theory, approximation algorithms, and algorithmic game theory. And also to complexity theory, where he has established with Les Valiant the hardness of unique solution instances of NP-complete problems. And more recently, over the last 4 years, he has been working on algorithms for matching markets, which is precisely the topic of this workshop. And he has co-edited a book on this topic, which is going to come out so this is a promotion of the book, actually, going to come out early next year, Cambridge University Press. He's an ACM Fellow, a Guggenheim Fellow, and most recently, the prestigious recipient of the prestigious von Neumann Theory Prize of Informs. So, Professor Vazirani, please.
Thank you very much. And, So I also want to congratulate the organizers, all three of you, and for putting up a very relevant workshop for today's research areas. And thank you all for coming. Really appreciate that. So This is the short version of my talk title, Algorithms for Matching Markets. And if you look at matching markets, yeah, good, it works. Okay, their birth goes to 1962 with the groundbreaking paper of Gale and Shapley, introducing the stable matching problem and giving an algorithm for it. And ever since, the field has been connected to algorithms, straight off. And if you look at stable matching, basically, there are so many algorithms, polynomial time ones, around it. And the one thing to notice, by the way, here, is that this happened, this is a polynomial time algorithm that they gave for finding a stable matching. Everybody does that in undergrad by now. But the point to note here is that it all happened in 1962. And that's before polynomial time was even defined, because that was defined by Edmonds in 65. So in some sense, they threw a dart in the dark and it landed. And that's amazing, right? And not only did that land, but there are so many other darts that have landed. I'm still looking for more darts here, you'll see. Amazing problem. So if you look at the set of stable matchings and define a certain partial order, which I will not go into, but many of you will be familiar with it, you get a finite distributive lattice. That means that it supports the operations of meet and join. And normally, so it looks like something like this. So I want to talk about the two sides of this bipartition that's there in the stable matching instance. And normally, the terminology came from dating and marital matters, and then things changed a few years ago. And now it has come from, the two sides are called workers and firms. And the top and the bottom are distinct of this lattice. One is the worker optimal matching, and one is the firm optimal matching. And someday, I'm sure the labor unions will revolt and we'll have to give up this terminology and move to some other one, but until then, we are safe. And but not only that, but because it's a finite distributive lattice, you can use Birkhoff's representation theorem, which goes back even further. And what that gives you is a certain partial order whose upper closed sets are isomorphic to the stable matchings in this lattice. Okay, many of you know these things. If not, then there are chapters of our book on my webpage, and all of this is sort of completely covered there. So it turns out that in this case of stable matching, the elements of that partial order are rotations, and there can be at most n square of them. So this is a succinct representation of the lattice, which could be exponentially large. And using those rotations, we can go from the top to the bottom. Okay, so the rotations sit on these edges, and we can go from one stable matching to the other, from the top to the bottom, or anywhere to anywhere. Okay, so and all of these operations are polynomial time, believe it or not. And some people remark, okay, how come there are so many polynomial time algorithms here? And I always have a standard answer for that, because this problem comes from that gold mine. Okay, so on top of that, stable matching has fantastic game-theoretic properties, besides the stability, which says that this is a solution in the core. So Dubins and Friedman and Roth independently showed that the matching that you find is dominant strategy incentive compatible for the proposing side. Okay, and all of a sudden that opened up stable matching to a whole bunch of applications. Okay, what this means is that if you're doing a worker proposing stable matching, then no worker can gain by misreporting. Okay, and so I will have to. I don't want to be tethered to this laptop, but maybe. Okay, so that opened up stable matching to many, many applications. And one of the big ones was school choice, because what was being done earlier for school choice was not working at all. So in big cities, you have like 100,000 students who have to enter into elementary schools, and there are like maybe some thousand schools. And the way of giving preferences before was causing stress to the parents and the students because they were trying to game the system to get better admissions. And now, since telling the truth is the best option, they don't have to stay up nights to figure out how to, get better schools for their children. And so no student can gain by misreporting, and suddenly everything becomes simple. And in fact, you know that the 2012 Nobel Prize in economics was given to Roth and Shapley for all this work. Okay, so I want to propose a new topic, a new problem on stable matching. And this was done in joint work with my student Tung Mai a few years ago. What we said is, suppose you take two instances of stable matching which are nearby. Okay, what do I mean by nearby? That means that you have A as the original instance, and it has some set of stable matchings MA, and you have one worker changes her list, okay, and you get an instance B. Everybody else has the same list, the preference list. The question is, can you get a matching which is stable for A and for B both? Seems very, very basic, right? How can it be more basic than that, right? Okay, so this was, we studied, Tung Mai and I started studying it, but we had to go very slowly because it's not easy to answer this question. And the first thing that actually we tried was swap. Just a worker swaps two firms, okay? That worked out. So then we said, let's do a shift. A worker shifts one firm from here to here. And you cannot shift back for reasons that are, because there's a certain asymmetry in stable matching. I can go into that later. But so allow an arbitrary shift. That means you can start from any of the n places and go to any of the n places, and this can be done for any of the n workers. So there are n cube shifts possible. And so you're given an instance B that comes from these n cube possible shifts, and you want to matching that stable for A and B. And what we showed is the following. So let A intersection B be the intersection of the two sets of stable matchings, and A minus B be the difference of the two sets. And what we showed is that these two, MA intersection B and MAB, are both sublattices of LA under the same meet and join operations. And as a result, we got a polynomial time algorithm. And then more recently, with Gangam, who is here, Rohit Gangam, Nitya Raju, and also Tung Mai, we said, okay, we want to do more. Instead of a shift, we allow arbitrary permutation. Well, the things get more complex, much more complex, and MAB is not necessarily a sublattice of LA, but it is a joint semi-sublattice of LA. So again, using these structural properties, you get, again, polynomial time algorithms. Yeah?
So does this intersection always not?
No. You can tell whether if the intersection is empty, the algorithm will say so. Yeah, good question. Yeah. Okay. And why do we care about two instances like that? Well, what is incentive compatibility? One worker misreports. That means that's how you get a second instance. And we have some applications which you might consider kind of frivolous. Yeah, and we do too. And we have another application which is not that frivolous, but is still not okay to robust stable matching. And really, I think this is so basic a question that is calling for a killer app. Someday, hopefully, it will be found. And we know, of course, that when you have a basic question that has been answered, applications can come many years later. And I'll show you an instance of that in this talk itself. OK, so then these two students who are still with me, Tung Mai has gone off to work for Adobe, I think. So we said, OK, forget about nearby. We want to take two arbitrary instances, A and B, over the same n, of course. Number of workers and buyer firms is the same. Then what happens? So this is the question we asked. Is A intersection B a sublattice of LA and LB? Of course, if it's empty, we can tell. But so if LA and LB have stable matchings in common, then look at that set of stable matchings. Is it a sublattice of LA and LB, okay, in the meet and join of A and B respectively? And they can have different meets and joins. We have many examples of that. We studied many examples, all the way to, I don't know, 8, 10, n equal to 8, 10 or so. Beyond that became more and more difficult. And we also really hit this question hard. In this example, what you have is A gives rise to this lattice, B gives rise to this lattice. The set of stable matchings is the same. It's M1, M2, X1, X2, Y1, Y2. But you can see that the join of M1 and M2 here is X1, meet is X2, here is Y1, and here is Y2. Nothing to do with X1 and X2. Okay? So there were places where the joins and meet was the same, or the meet was the join was the meet. But here they have nothing to do with each other. And still, of course, the intersection is because the intersection is just the same thing. It's a sublattice in LA and LB. Well, so why even answer this question? Well, it looks good so far, but let's see why it becomes even a better question. And the reason is that the stable matching lattice is universal. In what sense? In the sense that it's working now. Okay, in the sense that if L is any finite distributive lattice, then there's always a stable matching instance A such that the lattice of A is isomorphic to L. So in that sense, it captures all stable matching, all finite distributive lattices. Okay? So if the answer to that question that I put up in the last slide is yes, then we get a very big theorem about finite distributive lattices. Namely, if L and LB are two finite distributive lattices over the same ground set, in this case, these are perfect matchings of size n, then their intersection is a sublattice in LA and a sublattice in LB in their own meets and joins. Wow. Right? I mean, such a basic question about such an old topic. And of course, if we had answered it, this would have been the whole talk, right? But I'm presenting 2 more papers, so our hopes were up there, and then they came crashing down with a counterexample that was n equal to 15, I guess. So there we go. Sometimes not everything works out. Okay, so I'm going to switch gears and go to the next paper. And this is Hillen-Zickhauser is a classic mechanism in economics. The economists are, I don't know if you have any here. Oh, yeah. I mean, they are completely in love with this mechanism. Why? Because it's based on pricing. What does pricing mean? That means that you try to achieve parity between supply and demand, as simple as that. And that's a very big thing in economics because it gives rise to many nice properties about the allocations. Pricing has been studied for a century in economics in general equilibrium theory, which was always considered its crown jewel and sort of not in vogue anymore, but until a couple of decades ago, it was very much in vogue. So this is for a one-sided matching market, and what that means is that you have goods and buyers and goods, okay, and it's using cardinal utilities, unlike stable matching, which uses ordinal utilities, preference lists. Here you have real numbers giving the utility of I for agent I for good J. And it's a one-sided matching market. That means you're given n agents and n divisible goods, and you have to match them one-on-one and make sure the allocation is a good one. And here are some good properties of Hillen-Zickhauser. It's Pareto optimal, it's NB-free, and it's incentive compatible in the large. So very nice properties, but we want one more property, right? What's the other property that we want? Chandra has a big smile on his face, and I know what he's thinking. Is it in polynomial time, right? Okay, we'll come to that question. But let me first show you how the mechanism itself works. First you make goods divisible. So I said you're using pricing, and to use pricing, you have to have divisible goods. I mean, I don't see, with indivisible goods, it's almost impossible to do pricing. So you make goods divisible. So each good is 1 unit of probability shares. each agent has $1, and now you find an equilibrium. So prices and allocations such that if each agent gets 1 unit of probability shares, okay, for $1, that maximizes her utility, her best bundle of goods, but it has to be 1 unit because we have a matching market. And that's how it differs from a normal market, okay? Then that's called an equilibrium. And you may say, okay, there are 5 buyers, all of who want good 1, and they don't want any other good. How will it work out? Well, then the onus is on the prices. The price of that good will be so high that for $1, each one will get only 1/5 of the good, and then there is always a zero price good. We know that in this market. And they'll get the rest from the zero price goods. And so you get an equilibrium. In fact, so one thing to note is that now, so you had 1 unit of probability shares in the goods, and they are transferred into 1 unit of probability shares over the agents. So you have a fractional perfect matching. But you want to give the goods in an indivisible way to the agents, so you have to round it up using randomized rounding and using the Birkhoff-von Neumann theorem. That's polynomial time also. So that's how you get the allocation. But of course, Hieland and Zecauser prove using Kakutani fixed point theorem that this equilibrium does exist. Great, it exists, but can it be found in polynomial time? And at first, I always felt it was Jugal Garg actually asked me this question a few years ago, and I always thought this should be in polynomial time. Why? Because perfect matching is in polynomial time. Linear Fisher market, when you have no size restrictions on the agents, is in polynomial time. That was, in fact, the first market model for which a polynomial time algorithm was given. So it's a marriage of these two. So why shouldn't these two polynomial time algorithms result in a polynomial time algorithm for HZ? Okay? And then there was a big stumbling block. Linear Fisher markets satisfy weak gross substitutability. I will not go into that. You can always talk about it over lunch. This HZ does not satisfy weak gross substitutability. So if you have a Fisher market with piecewise linear concave utilities that does not satisfy weak gross substitutability, and this polynomial time algorithm doesn't extend. In fact, it's PPAD complete. So this is where I, of course, had to involve Mihalis Yannakakis, who's the master of reductions. And the first question we asked is HZ PPAD complete? And a prerequisite to showing even membership in PPAD is that there should always be a rational equilibrium. And rational is not an English language word, it's a mathematics word here. That means it can be written in rational numbers. Of course, it has to be rational also. So, theorem, equilibrium can be irrational. That means PPAD is not the right class to capture this. Actually, then we showed that it is fixed. The membership is in fixed P, but that's another story because we didn't show fixed P hardness. But we did show that approximate equilibrium is in PPAD. And then showing hardness here was very hard. And we conjectured that it's PPAD hard, and it was later shown in this work. Okay. So what does this mean? It's PPAD hard, but what does it mean for real computation? What it means is that the only way we know of computing an HZ equilibrium is whatever was known for a very long time, algebraic cell decomposition, which is basically an exhaustive search. And you can basically do it for n less than equal to 10, or maybe even 6, I don't know. So how many markets have 6 buyers? Very few. How many markets have 10,000 buyers? Very many. So are we stuck here? And there's more bad news. So Hieland and Zecauser then generalized their model to the exchange version, where agents have initial endowments, and then they sell these initial endowments at going prices and get their best endowment. That's called the RFW market model, which is what is really studied in economics. Okay, and so they defined this, and they showed an example where equilibrium doesn't even exist. And that's where the train came to a halt. Okay, why do I say a train? Because if you look at general equilibrium theory, which, as I said, was studied for not 1,000, but 100 years, maybe not 1,000 years. It doesn't go back to the Greeks. I don't think it goes back to the Greeks. We never know what the Greeks can pull up. So general equilibrium theory has so many models for all kinds of situations and really a rich collection. And they're all, of course, cardinal utility based. But then if you look at matching markets under ordinal utilities, again, you have many models. You must have heard of some of these models, and they're all polynomial time. Okay, but here things were stuck completely. We just got HZ and nothing more, and even there we have no way of using it. And so just to compare ordinal and cardinal utilities, ordinal are, of course, easy to elicit because you just ask them for a total order. And cardinal are more hard to elicit because somebody has to think, okay, do I like this to the extent of 2.156 or 2.157? I mean, you have to ask them for these numbers. And then, of course, but then you get better allocations as a result. Am I going too fast, or is it okay? Sorry? Yeah, so HZ is, approximate HZ is also PPAD hard. So that's gone.
Do
Yeah.
you think there are, like, for SPLC markets, we have complementary pivot algorithm?
That's a good question. At least the equilibrium should exist first before you start to find it using complementary pivot.
Sorry?
Here, even equilibrium.
The
Fisher and HZ. HZ, approximate. Very good question. It's a Ruta Mehta question. Yeah, so awesome question, yeah. I don't know. Okay, so is there a recourse? Okay, obviously we want to get around this whole intractability. What can we do? So many years ago, now it turns out to be a decade ago, everything goes by decades now. So for this setting of a linear ROW market model, what I said is instead of pricing, why don't I use Nash bargaining? Okay, and I managed to get not only an algorithm, polynomial time, but in fact a combinatorial algorithm based on flow. This is just pulling up the linear Fisher market up one level. That's how it happened. So when this whole intractability came about, then I started thinking about the use of Nash bargaining for matching markets. And what's Nash bargaining? So you have two players. One has a home in the mountains, and one has a home on the beach. Like I'm in Irvine, so 20 minutes away to the west is the beach, and 2 hours away to the east is the mountains. So there are two such agents. And now they want to share their homes, vacation homes. And you look at all possible ways of sharing those homes. And for each way of sharing the homes, you get a two-dimensional utility vector. How much does player 1 get? How much does player 2 get? And you plot that. So like, this is what player 1 gets by getting both homes for the whole year, and what player 2 gets by getting both homes for the whole year. And each of these points is two utility points by some sharing. We don't care about the sharing. We just care about the feasible utility vectors. Okay? And I'll assume that this is a convex compact set. And there's a disagreement point. This is the utility that player 1 gets by just keeping her mountain home. And this is the utility that player 2 gets by just keeping his beach home. And obviously, both of them will say, I don't want to go below that utility. Otherwise, I'm not participating in this game, right? So you want something, a solution that's in this region. But the question is, there are plenty of points there. Which is the right point, right? Which is the right point? And Nash says the point must satisfy four very reasonable axioms: Pareto optimality, invariance under affine transformation, symmetry, and the last one is somewhat suspect: independence of irrelevant alternatives. And if you assume these four axioms, then using a fantastic proof, he showed that there's a unique point that is the right solution. Oops, sorry. Yeah. And that unique point, which has to be, of course, on the Pareto boundary, is the one that maximizes this product. V1 minus C1 times V2 minus C2, where V1, V2 is over this whole set, S. Okay? So this is the unique point at which they should do the bargaining. Beautiful, right? Now, if you look at what he's saying, this, and moreover, it generalizes to n players. Same way. If you look at, so this particular function is log concave. So if you take its log, you get a concave function. And so you're maximizing a concave function over a convex set. That's a convex program. You can solve it in polynomial time. Wow, so Nash bargaining is in polynomial time. Well, or approximately solve it. And so I got together with a student from the business school, and we have a paper in ITCS, I think, of this or last year, I don't know, where we give Nash bargaining-based models, matching market models. And Mostapha Hosseini is still an expert on programming up convex programs and running them very, very fast. And he did a whole bunch of experimental results. And as a result, we got a very rich collection of models, all solvable in polynomial time. That is the basic one, the first one that corresponds to HZ. That corresponds to the exchange version, which is not possible with HZ. That corresponds to piecewise linear concave utilities, but as a matching market. That corresponds to a two-sided matching market. And what, lo and behold, if you have n equal to 2,000, he managed to solve this in 1 hour on a PC. Okay, so these markets are not hard. And remember that with HZ, you couldn't even do it with n equal to 10, even for a one-sided matching market. Two-sided, of course, is much harder. And then we even got a non-bipartite model, which can be used for the roommates problem. And this last model was given in another paper with Panayas and who's a faculty at Irvine, and Thorben Tropes, who's my very senior and fantastic graduate student. And we gave, so the previous work was all experimental without looking at running times, but here we gave algorithms based on multiplicative weight update and gradient descent with proven running times. So you're going to present this. I was going to ask a question, but you're going to present it on this slide. No, I'm not going to present these algorithms. We can talk over lunch.
I was going to ask, how does this relate to pricing?
No, so yeah, good. How does it relate to pricing? Oh, very good. Oh, yeah. That's a Kamesh Munagala question. Okay, fantastic. So why go from pricing to Nash bargaining? Does it even make sense in a theoretical economics from that perspective? Does it even make sense? Is there even a connection between these two? And there is a connection, actually, a pretty nice connection. So if you look at the Fisher model, linear Fisher model, and you can either solve it using pricing or using Nash bargaining, okay? Like I did linear ROW model using Nash bargaining, then linear Fisher is only easier. Both of these use the same convex program, namely the Eisenberg-Gale program, which is absolutely a classic. Everybody knows about it. I even dream about it. Okay. So it's polynomial time. And it goes back to the same one convex program. Then if you throw in unit capacities on the agents, this model with unit capacities on the agents, then the two problems diverge. Pricing becomes HZ, And Nash bargaining becomes the first model that I give you in a few slides ago. Okay. So okay. Lastly, H3 also satisfies envy freeness. Nash bargaining does not, but that doesn't mean that you can give all the goods to one agent. Nash bargaining has to satisfy what's called proportionality, so nobody is really cheated here. But it's not as strong as envy free. But then if you have all these properties and you cannot use it for n equal to more than n equal to 8, what are you going to do with the properties? Okay, so that's the dilemma we are in, always. Okay, so we move on to the last work, and matching markets. And I always feel like one should classify them into these three classes. Pre-internet, the classic ones, matching residents to hospitals, students to schools, kidney exchange. These two are, of course, based on stable matching. This is based on maximum matching. Everything goes back to that gold mine. Then came the internet, and many more markets got defined. And this time, they really occupy some fraction of the economy, like the AdWords market, which is a multi-billion-dollar market that supports Google and gives us search and YouTube and Gmail for free. That's the reason for that. I'll talk more about that. And Upwork, which matches workers to employers, display ads, and so on and so forth. And then came mobile computing and many more new markets that we're all using all the time on our iPhones. They came up. And the one feature about these, which is distinct from these, is that they are online. Every one of these, in some sense, is online. It could also be offline, but it's certainly so. So in AdWords, the keywords are, the searches are coming online, and they have to be matched to advertisers. I'll show you more about it. Here, workers and employers are coming online, and they have to be matched maybe in some time window or something. Here, writers are coming online, and two of them have to be matched. So this is like non-bipartite online matching. And okay, there's one matching market that's not in this list. It's the one that you're probably most worried about, unless you're too young and then you're worried about this one. Academic, yeah. So if you're about to graduate, you worry about this one, and that's not here because here every professor you hire is a one-off. You cannot automate this thing. And just as a curiosity, here's a matching market that I came across in one of my travels at CMU. Somebody told me they had launched a matching market. So when you have these conferences like NeurIPS where you get 10,000 submissions of papers, just matching papers to reviewers is an ordeal that no human being can do, or a set of human beings can actually execute. So they have automated it into a matching market. But this is, of course, not online because papers don't come. Maybe papers can come online. I don't know.
Is that perfect matching?
No. Yeah, each paper has to be matched to several reviewers. So it's like workers and firms, because firms employ more than one worker. Okay, so this online feature is the big novelty about this second life of matching markets. And just like stable matching was the algorithmic backbone for the first life, it turns out there's this nice problem, online bipartite matching, which is the paradigm and its generalizations. They form the algorithmic backbone here. And that's what I want to talk about for the rest of the time, if I have any. So what is online bipartite matching? You have a bipartite graph over n goods and n buyers. You don't know the graph. You know it has a perfect matching, but that's also not needed. But let's just assume for simplicity you have a perfect matching. And the goods are sitting around. The buyers come one at a time with all the incident edges. As soon as the buyer comes, you have to match the buyer instantaneously and irrevocably to one of the goods she wants, which means that there's an edge to that good. And you want to achieve as big a matching as possible without knowing the rest of the graph. So that's the whole point. You have to make decisions based only on what you know. You don't know the future. um, it's certainly a captive, very convincing paradigm for life also. But let's not go there. It's very the way you analyze these algorithms is to compare against the best offline, and for deterministic algorithms, it's very easy to show that it's tight at a half. Every algorithm that is not going to give up matches for no reason, means that it's greedy, will do at least a half and at most a half. So then you have to use randomization, and that's the going algorithm, which is actually optimal in the sense that I'll say in a moment. So what is this algorithm? It's not the first algorithm you'd think of, but hopefully it's the second. What you do is you permute the goods randomly once, and let the buyers come one at a time. And as each buyer comes, you match her to the highest available good in that random order. But you don't re-permute the goods. Then it's lost. Then it goes back to a half, essentially. So permute the goods only once. So this is an algorithm that we gave when we studied, we being Karp and Umesh Vazirani and me, in 1990. And at that point, there were no dollar signs attached to this problem. And then no applications, and then suddenly everything starts growing under our feet. So this is what I had in mind, but that when you do something basic, hopefully it finds applications within your lifetime. Well, later is also fine, I think. So this is the competitive ratio. It's constant above a half. There's not much more room than a constant there anyway. But it's optimal using Yau's lemma. You cannot do better for any randomized algorithm. But the problem with this paper was that it had one small error, but more importantly, nobody could understand the proof. And then many papers were written to many, or at least 4, and then mine 5th, to simplify it. Okay, so I want to turn to the adverse problem, which is a generalization, one of the generalizations that I mentioned here, and then I'll come back to, of course, online bipartite matching also, because that story has to be finished. So this problem comes up in the when you in ad auction marketplaces like in Google. And what is it? So when you type a keyword like Vioxx, this is a view of Google from decades ago, when this thing was actually happening all the way back. Now there's a slightly different view. So you type a search query like Vioxx, which is a drug for inflammation, and Google gives you search results, and here you also get advertisers who know you're thinking about Vioxx and would like to sell you something related to Vioxx. Okay, and you would have expected here pharmaceuticals who want to sell you some more Vioxx, but turns out all of these are lawyers. And why? Because Vioxx was causing heart problems to the patients who were taking Vioxx, and these lawyers, before those patients were dying, they wanted to attract those patients and make some money off of some lawsuits. So these lawyers were actually bidding somewhere between $50 and $100 to be here. And if you click here, whatever they bid, let's say, approximately goes to Google's account, and that's how Google makes its money. If it were a pharmaceutical, you could have bid maybe 20 cents. But so you put on a high bidder here, of course. But that's not the end of the game. You just don't put only the highest bidder. Reason that when these advertisers, and there are thousands of advertisers, there are literally millions of keywords. Okay, so when an advertiser goes to create a campaign with Google, they also declare their daily budget, beyond which they don't want clicks, because they don't want to go bankrupt in a day. And once the daily budget enters into the picture, it's not you don't just do greedy. So this, I have 3 minutes, or? Yeah.
Over, but
okay. So I just want to say so this problem came to us in 2005, and it's a generalization of online bipartite matching. One can see it. It's a generalization. And at that point, we could not extend ranking to this problem, to AdWords. But we extended B matching. But with this simplified proof, and that was using the budget, the leftover budget of the advertisers in a very key way. So with this simplified proof, I said, okay, why not go and extend ranking directly to AdWords under small bids, because under large bids it's still wide open. The whole question is, there was a Fox paper going 0.5016, okay, and 0.5 is obvious, okay, but that we don't know how to go beyond 0.5016. So AdWords under small bids, can you extend ranking to that? And this is a more elementary approach, and as a result, it gives what is called budget obliviousness, which means that it can be used in auto bidding platforms. And this is a very nice paper from Google that talks about algorithms for auto bidding platforms. And turned out I could do a subcase, which is intermediate between online bipartite matching and this AdWords called single valued. But when I went to the entire problem of AdWords under small bids, one critical fact failed in a very big way. In a very big way, but it's a subtle failure. The main work I did was in the probabilistic part, and just to salvage that, I wrote a conditional theorem. I don't know how many people write conditional theorems in the paper, but I did, okay? And, but I gave experimental results to support, because it's hard to make this thing fail. So most of the time it doesn't fail, so experiments showed that this is comparable to MSVV, and if that is indeed the case, then we have a nice algorithm that can be used, which is budget oblivious. And somebody has to go in there and remove this word conditional, not with an eraser, but by using their mind. Okay, so advantage is that you can use auto bidding platforms, and 2 undergrads from UCI did experiments to show that this algorithm is indeed comparable to MSVV. And that's it. Thank you. I know one question that everybody asks, and I wanted to give you the answer there itself, which is, why don't you use historic data, right? Why do you need this algorithm, right? So actually, it turned out Arnek Mehta came by UC Irvine 2 weeks ago and gave really a fabulous talk on auto bidding and AdWords and all that. And he stated that the answer to this question is yes and no. You can be using historic data, and you cannot. Yes, because when you have large advertisers, same things repeat over time. So what happened yesterday will happen today. When you have small advertisers, like the maid who wants another job to do, or a shoemaker that has too many shoes and now has to sell them off, for those small advertisers, everything changes on a daily basis. So there, for them, you start with the historic data as your in this business of bid scaling. You start with the historic data as your right parameter for the bid scaling, and then you let it run over the day, and you see what happened, and that will determine how bid scaling comes in. And so bid scaling, which came from our algorithm, is still used. Okay. No patents were filed, by the way. Okay. So, any other questions?
Okay. Yes.
So for the matching intersection stuff, is there a sort of is there a polyhedral answer or something? Like if you look at the stable matching polytopes and take their intersection, can you get?
I think it's a lattice question more than polyhedral.
So I mean, it's a polynomial time question, right? Does there exist?
So you're saying that the polytope of A and B will also intersect, and so using the polyhedral intersection, can you find out a matching in the intersection of the 2 polytopes?
Or if it's empty or not?
Huh? Or is it empty or not?
Yeah.
It's a very good question and worth looking into. We looked at it from the viewpoint of lattices, but yeah, it's worth looking into.
Okay.
And very much, yeah. But yeah, I mean, Yeah, I mean, so stable matching has these two approaches. One is deferred acceptance, and one is an LP approach, and one should be looking into both. Yeah.
Okay, thank you.
Thank you. Thank you very much.